Hello students, good afternoon. How are you all? So today in our doubt solving session, we are seeing influence line diagram for beams. Okay. So influence line diagram, what is the basic of it? What is the concept behind it? What are the theories behind it? So everything you can find it in Ekeeda app. So please subscribe to Ekeeda, install Ekeeda application, okay, and subscribe to this subject to get all the details. So today we are going to solve a problem for a overhang beam. Okay, overhanging beam we are going to consider, and we are going to draw influence line diagram for different reaction shear force for different points. Okay, now what is the influence line diagram? So where we are drawing it? So influence line diagram, you can see here this particular simply supported beam, and at C point, if you are interested to find draw influence line diagram. Okay, for moment if you have to draw, so this will be a influence line diagram, ILD, for moment at C. And when we consider load ordinate, okay, suppose we are considering load at some point here, so corresponding ordinate, okay, that shows its value. So influence line diagram drawn for various stress resultants like reaction, shear force, bending moment, torsion at specified points. And if we say that influence line diagram for stress resultant is the one in which ordinate represents the value of stress resultant. We are also going to solve a problem on this if time permits today. Then we'll take, otherwise we are going to consider a overhanging beam problem. So let's see a question. So we are going to consider this particular beam. So let me write question. This is a typical overhanging beam. Draw a ILD, draw influence line diagram for number 1, reaction at support A, then number 2, reaction at support B, then third, there will be a point D on a beam that I'll show in the diagram now. So we have to find out shear force. So we have to draw influence line diagram for everything what I'm writing. So shear force at section D, then bending moment at section D, and then shear force at section E, and bending moment at section E. Okay, so we are going to we have to find out influence line diagram for these cases. Now what are these points? Let me just draw the beam, and we are going to need this diagram again and again for this influence line diagram. This is overhang beam. So this is one support A, and there is one support B here. So we can show it by reaction. So let's call it as A, point B over here. Then there is a point, some point D here, where it has been asked to us that find out shear influence line diagram. We have to draw shear force at section D and bending moment at section E. So that is D, and this is E point. There is some point E, and the last point is C. Now what are the dimensions? Dimensions are, this is a Z distance, and the total span over here, this is L, and this particular length is A. This particular span, this is A1. So this is Z, this is L, this is A, and this is Z1. Okay, so this is a typical case of overhanging beam. Now number one, we have to find out what is the influence line diagram for reaction at support A. So for that we need to consider, to calculate the influence line diagram for RA, we need to find out what is the reaction at A first. Okay, we also need to find out what is reaction at B. So for that case, we need to consider the positioning of unit load. So we have to show the unit load where it will be acting. So for that, let's consider uh, overhanging beam with positioning of unit load. So what I'll do, I'll just draw it here. So first I'll show the positioning of unit load in between AB, and then positioning of first I'll show unit load here, then I'll show unit load in between DB. Okay, so AB region and then BC region. So two regions are there over here. Okay, to consider the unit load. So AB and BC. Okay, AB is a for this particular overhanging beam. These are the supports A and B, and this is the overhanging part. So let's draw the to get the solution. We have to draw this diagram first. So let's draw this to show the positioning of the unit load. So just I am redrawing this diagram quickly. This is our point B. This is point C. So this is A, D, B, C, and this is some point E. Okay, now here this is AB. So all dimensions we know, so I'm not writing it again. Now let's consider when unit load is in portion AB. Okay, when unit load is in AB, anywhere in AB. So let's call this as unit load 1, and wherever we are drawing, we have to show that the distance from the unit load to the support A, that is X distance. Okay, now let's start doing the calculation for influence line diagram for RA. Now when we want to calculate influence line diagram for RA, okay, reaction at A, so that is our first case. So here let's do the calculation. So to calculate the reaction at A, we want to calculate what is the reaction at A first. For that, let's consider moment at support B. So when you consider moment at support B, so that is equal to 0. So let's calculate. So how will be the moment at B? So we will write RA. Okay, if moment about this means load into perpendicular distance. So RA into L, because this total length is L, minus 1 into this distance L minus X, right? So I can write it at this side. So 1 into L minus X. So here I can write RA is equal to L minus X by L. Okay, so I got the reaction here. Now this X is varying from 0 to L, right? So when X is equal to 0, so substitute X equal to 0 here. So in that case, we are getting RA is equal to L minus 0 by L. So we are getting the answer as 1. So this is 1. And when X is equal to L, in that case we are getting RA is equal to, it will be 0. Okay, so this is the case over here. So now once we get this, now let's bring this unit load to BC portion. Okay, let's bring it to BC portion. So when you bring, so here, let me just write it in one line that unit load is in between AB. So in this case, unit load is in between AB. Okay, now let's consider when unit load is considered is in between BC. In between BC. In this case, then how will be the is this unit load is coming here somewhere, okay, in between BC portion. So in this case, when one load is here, then again find out what is the moment at B support, okay. So when this unit load is there, again our reaction, okay, Ra into moment about B, so we will write the same equation. Again, if you write the same equation, MB equals to 0, so we will again write, we can write Ra into L, right, load into perpendicular distance, because moment at B, but unit load is not acting here now, unit load is acting in BC region. So now we have to consider 1 into this perpendicular distance. So how we will write? So we know that this particular region, that is A, this distance is A, and the distance between unit load and C point, that is X. So our equation will be Ra into L is equal to minus A minus X by L. Okay, minus A minus X by L. Okay, so this is our, because if you see this moment, both of them are in same direction. Okay, this is also making a clockwise direction, this is also clockwise, so that's why it's negative here. So here again we will put the limits in this case. So let me take a next page. So at x equal to 0, now we have to substitute value. Okay, so Ra is equal to, our equation was minus A minus x equal to 0. So 0 by L, so we are getting minus A by L. And when x equal to A, Ra will become A minus A, it will be 0, right? So it will be 0. So then now let us draw influence line diagram for Ra. Okay, so whatever values we have got, we have to simply plot them. 1, 2, just see the values 1, 2. So we have to see, we have to simply plot these values, and that will be our influence line diagram. So I am again redrawing it, redrawing the beam. So this is our some point A, this is our point B, and this is our point C. Okay, now let's see, at x equal to 0, Ra is equal to 1. Okay, so let's draw the ordinate 1 over here. This is the 1 ordinate. Okay, now here at we started calculation from this side here. Okay, so that is the 1 ordinate, and at this point it is 0. Now when you start calculation from this side, at x equal to 0, ordinate is minus A by L. So let's draw this. So this ordinate is minus A by L, and this ordinate is 1. Okay, so this is our, this is positive, this is negative. So this is our influence line diagram for Ra. Okay, now let's see influence line diagram for Rb. So that is a second influence line diagram for Rb. So when we have to calculate influence line diagram for Ra, means we have to calculate what is reaction at A. Okay, so that time we have considered moment about support B. Now we have to calculate what is influence line diagram for Rb. So here let's consider, now let's consider unit load. Unit load is in portion of AB. Okay, if you consider this overhanging beam, so unit load is in portion AB. The same beam we will refer. Okay, it's first unit load is in portion AB. So now let us consider the moment about support A. Okay, so how we will write equation moment about support A? So RB into total length L and 1 into X, that will be our equation. So this is anti-clockwise and this is clockwise. So we consider clockwise as positive, anti-clockwise as negative. So with that sign convention, our equation will become, let's consider moment about A is equal to 0. So RB into L is equal to 1 into X. So RB will be equal to X by L. So once we get this equation, then we have to put the limits. Okay. So when at X equal to 0, our RB will become 0 by L equals to 0. And then when X equal to L, RB will be equal to L by L. So it is 1. So we got the values here. Okay. What are the values for RB that we have already got here when our unit load is in portion AB. Now let's see when unit load is in BC. Now when our unit load is in BC portion, when unit load is in BC portion and when you have to consider moment about A, so just see here how we will write equation. RB into L, okay, this is the total length, RB into L, and 1 into, we need this total distance, right? So 1 into L plus this distance we have to see, right? This distance. So how will be this distance? A minus X when we'll do. So we will get this distance. Okay, so that way we will write the moment equation here. So let's see. So here moment about A is 0. So RB into L, okay, RB into L, that is clockwise, and this is 1 into the total distance. So I am writing it equals to 1 into L plus A minus X. So RB value we are getting as L plus A minus X by L. Now again we'll put the limits. At X equal to 0, RB is equal to, when you put X equal to 0 here, then it will be L plus A by L. And when X equal to A, in that case, when we substitute, is equal to 1. Okay. So we got these values 1, 2, 3, 4. Now when you see the values here, it is 0, it is 1. And here it is L plus A by L, means it is little more than 1, right? It is more than 1. And this is the 1 ordinate. Now let's draw the influence line diagram for RB, reaction at B. So I'm drawing again the similar line, overhanging beam. So this is A, this is B, this is C. Okay, now let's see the values. So when at X equal to 0, RB is 0 here, right? At X equal to 0, RB is 0. And at X equal to, X is varying from here, right? 0 to L. So at X equal to 0, X is 0, so RB is 0. And at X equal to L, RB is 1. Okay, so here it is 1. So this is 1 ordinate. And at X equal to, from here when we do the calculation at X equal to 0, it is L plus A by L, and at X equal to A, because this is the A, so it is 1. Okay, so we have already drawn 1. Now here at X equal to 0 means from this side when unit load was in this portion, so that is L plus A by L. So let's draw that ordinate and let's connect these points. So this is 1. This is L plus A by L. This is 0. So here we have covered, completed second part of our problem. So we have drawn influence line diagram for reaction at B. Okay. So once we are done with it, now let's move to the third part. What is the influence line diagram for shear force at D? Now we have to see here that a point is given at D and E. So we have to find out what is the influence line diagram for shear force and bending moment at D, and what is the influence line diagram for shear force and bending moment at E. Okay, so these two parts we have to cover, means we have to cover this 4 calculations now. So let's see what is the shear force at section D. Influence line diagram for shear force at section D. So here when we want to calculate shear force, influence line diagram for shear force at section D, again we are going to refer the same diagram. So our diagram goes like this. So this is a beam. I'll draw a little small diagram over here. So this is A, this is B, this is C. Now there is a point D. This is RA, this is RB. Okay, so this is our beam overhang, and this is the overhang. BC is a overhang beam. Now let's see when unit load is in portion AD. What is that? We have to find out shear force. Influence line diagram for shear force at D. Now let's see when unit load is in this portion AD. So unit load is in portion AD. Okay, so we can write what is the shear force. What is the shear force at D? Okay, what is the shear force at D? So when you calculate shear force at D, so RA and then -1, so ultimately you will reach at RB. Okay, so when you go like this in calculation, so finally you will arrive at RB. So what we will do, whenever unit load is acting in this region, we'll directly consider this reaction. Okay, so let's see shear force at D, that is equal to minus RB, and RB value we already know. Okay, it is minus x by L, that is minus x by L. So here unit load is acting over here. Now our x limit we know, at x equal to 0, shear force, okay, shear force at D or f of D, force at D, that is 0 by L. So it is 0. And when x equal to z, then shear force at D is equal to, x is simply replaced by z. Okay, because this distance we know, this is z, right, till the point D. In our first diagram we have drawn it as z. Yeah, this is z. So z by L minus z by L. Okay, that x equal to z, fd is equal to minus z by L. So this is when our unit load is in portion AD. Now let's see when our when this unit load is in dB. So when unit load is in portion dB. So now the second case, it is here. Okay, let's forget about this part. So when unit load is in this portion, they will consider reaction RA. So in this case, shear force at D is equal to RA. So RA we know already with the previous calculation, RA is equal to L minus x by L. So once we get this, then we have to simply substitute the limits over here. So L again, this was Z portion, and this is 1. So so x is varying here. So at x is equal to z, okay, when this x is equal to z, because 1 is varying from D to B. So when x is equal to z, at that point substitute x equal to z here. So shear force will be L minus z by L, right? And when x is equal to L, then shear force is equal to L minus L by L, that is equal to 0. So that is our, when x equal to L, shear force at D is equal to 0. So that is one case over here. The value what we have got over here. Now let's see when unit load is in this portion. Okay, now let's see the let's consider the unit load is in this portion. So this is point, this is unit load at some point between B and C. So when unit load is in BC, okay, in portion BC, then shear force at D is equal to RA. So that is when it is in BC part, okay, when this unit load it is in BC part, so it can be anywhere between B and C, okay. So we have to consider shear force, what is happening at RA, because our question we have to find out influence line diagram for shear force at section D. So when unit load is in this portion, then what will happen at D? Okay, so that's what we have to calculate. So when unit load is in B here in this BC portion, then shear force at D will be nothing but RA. Okay, only RA is there, and RA is equal to minus of A minus X by L. That is our previous calculation. We already have the reaction. So when X equal to 0, shear force at D is equal to, when you keep 0 here, it will be minus A by L, and when X equal to A, shear force at D is equal to A minus A, so it will be 0. Okay, so here we got all these values 1, 2, 3, 4, 5, 6. So we have to plot these 6 values, and that will become our influence line diagram for shear force at D. So let's draw it. Now let's see what are the values. So if you see here, here at X equal to 0, okay, shear force is 0. So at this point 0, and then at point D it is minus Z by L. Okay, so this is some point D. This is A, this is D, this is B, and this is C. So at D point, if we see, it is minus Z by L, and at D point again here it is L minus Z by L, so positive. So it is 0, so we have to go negative and then it will go positive. So like this our diagram will be. Okay, so this is our influence line diagram. And then what is happening at B point? So this we will plot here. This is 0. This is Z by L. This is L minus Z by L. Then at B point we have to see, again it is becoming 0 here, and at here it is 0, and here from right side when we see it is minus A by L. So it will be, we have to plot it here. So let's plot it. This is minus A by L. So we have to, so this is minus A by L. Anyway, this is 0. We got all the calculations. So simply we have to plot all the values, and this then we'll get it as influence line diagram for FD. So this is our influence line diagram for FD. So we have completed third part, influence line diagram for shear force at D. Now let's see influence line diagram for moment at D. Okay, that is a fourth thing to calculate. Influence line diagram for moment at D. Okay, now when we want to find out what is the influence line diagram for moment at D, so for this, let's again consider the same cases. When unit load is in AB, is in AD. Okay, so we will consider first unit load is in AD, then we'll consider unit load is in DB, and then we'll consider unit load in BC, like we have done for the shear force. Okay, unit load first we'll consider in this region, then in this region, then in this region. So let's write down. So when unit load is in portion AD, so in this case, what will be moment at D? So moment at D is nothing but when unit load is in portion AD. So if unit load is here, so what will be the moment at D? So how we will write? We can write a moment equation from this side or this side. So if you want to write from this side, then it will be simply RB into this particular distance, that is L minus Z, because total distance is L. So we can write it as L minus Z. So RB into L minus Z. So RB is X by L into L minus Z. So at x equal to 0, moment at D is equal to 0, and at x equal to Z, moment at D is equal to, it will be 0, right? At x equal to Z, moment at D will be, oh sorry, it will not be 0, it will L minus Z. Okay, so when unit load is in AD, so our values are this. So these values we will be plotting. Now let's see when unit load is in portion dB. When unit load is in dB. So in this case, so when unit load is in this portion, okay, so in this case, what is the moment at D point? Okay, so let's see what is the moment at D point when unit load is in dB. So that is nothing but RA into Z. RA into Z. So RA value we have L minus X by L into Z. So at X equal to Z, our equation M of D will become L minus Z by L into Z. Okay, if you can see here, this value and this value is matching, right? So it is the same point. So that is at X equal to Z, and when X equal to L. Why it is Z and L? Because now unit load is in portion dB. So that's why. Now substitute MD is equal to, when you substitute in this equation x equal to L, so this L minus L will become 0. So overall equation, it will give us a 0 value. So we can see at B point, x equal to L means at B point, it is moment is becoming 0 over here, right? Now let's consider moment unit load is in last portion, BC portion. So when unit load is in BC, so in that case, moment at D will be, when it is in BC, then again it is RA into Z. So that is minus of A minus X by L into Z. So here again X is, now it is from right side calculation. Okay. So at X equal to 0, moment at D will be minus of A minus 0 by L into Z. So that will be minus A into L, A by L into Z. And at X equal to A, moment at D will be A minus A 0. It will be 0. So now we got these values to plot. Okay. So, and then it will give us the influence line diagram for moment at D. Okay. So let's draw it, how it will look like. So this is our overhang beam. So this is our point A. This is our point B, point C. This is point D. So at this point we can see at when at x equal to 0, moment at D is 0. So this is 0 point. At x equal to Z, this is Z into L minus Z by L. Okay. So at x equal to Z means here we are getting a point. When unit load is in this region, then also we are getting this value. When it is in this region, at this point we are getting the same value. So let's join this point. Okay. And this ordinate it is, and then at this point it is minus, at this point it is minus A into Z by L, and this is, this ordinate, it is L minus Z by L into Z. Okay, so this is the case. So this is influence line diagram for MD. Okay, so we have solved a fourth point. Now we are left with only influence line diagram for shear force at E point and moment at E point. So the fifth point, influence line diagram for shear force at E. Okay, so shear force at E. Let's see. Now for this portion again, let's consider. Let's consider when unit load is in portion AB. When unit load is in portion AB. So when unit load is in AB portion, in that case, if unit load is in AB portion, then what will happen at this point? This is the E point, right? So nothing will happen. No shear force will come at this point. And even when the unit load is in portion BE, okay, so in that case, when load is in portion BE, okay, if it is also in this case, then also shear force will not be there. Okay, so both the case, let's write down. When unit load is in portion AB, in that case force at E is equal to 0. And when unit load is in portion BE, in that case also force at E will be equal to 0. Now when unit load is in portion EC, the last part of the overhang, when it is in here, okay, if unit load is in between EC, then definitely it will carry a shear force of 1 unit. Okay, it will be constant in this region EC, because load is acting at this point. If load is acting at this side, nothing will happen at E, but when load is acting at this point, then there will be a shear force here. Then in that case Fe is equal to 1, and that is constant. So therefore influence line diagram, so with this we can draw the influence line diagram for shear force at E is, so first draw a beam, overhang beam, and it is only in this portion. This is A, this is B, this is C, and this is E. So if you see here, the point influence line diagram, is it only between EC. Okay, so this is shear force at E. Now the last part of the problem, okay, that is influence line diagram for moment at E. So here again, if you see this part, when load is in AB portion, when unit load is in BE portion, so in that case shear force was 0. Similarly, when load is in this portion, when load is in unit load, when unit load is in portion AB and BE, so it will not create any moment. Okay, it will not be a cause or reason for the moment at E, so that will be a 0. So when this load is in portion EC, when the load is in portion EC, so in that case moment at E, okay, when the load will be in this case, then moment at E will be, it will be nothing but let me just show it with diagram. So when load is in this portion, so this distance is x, right, and the total distance is a. So 1 into moment about E we are doing, so 1 into, sorry, this is not a, this is z1, this is z1, so 1 into z1 minus x, okay, because we need this distance. excuse me. Okay, so when load is in EC portion, then moment about E point will be 1 into this perpendicular distance, and that distance will be Z1 minus X, 1 into Z1 minus X. So moment at E, we can write it as minus 1 into Z1 minus X. Okay, this is overhang. It is overhanging portion, so this is like it's a hogging, right? It's making a hogging, it will be a hogging shape, so that's why it is a negative part. It's like a cantilever. So here, once we are done with the equation, then again use the limits. At x equal to 0, moment at E is equal to, when x is 0, it will be minus Z1. And at x equal to Z1, moment at E will be equal to 0. Okay. So these are the values we have to plot for to calculate influence line diagram for moment. So let's draw it. So this is our beam. This is A. This is B. This is C, and there is a part E. So here we know it is Z1, and that is negative. So it will go down. Okay, that is going down. And this is 0 here. Okay, it is 0 here at this point. So at x equal to 0 means at this point it is Z1. And at x equal to Z1 it is 0. So this is Z1, this is 0. So this is our ILD for ME. So this completes our problem. So in this particular problem we have seen influence line diagram for a overhanging beam. Okay, so we have calculated, we have drawn influence line diagram for reaction at support A, reaction at support B, then shear force at section D, bending moment at section D, then shear force at section E, and bending moment at section E. Okay students, so hopefully hope you understood this particular problem, and in case of any difficulty, you can reach me at the number. You can see the my number, WhatsApp number appearing on the screen, and you can approach me through that number. In case of any difficulty, you can subscribe to the channel. Okay, thank you for listening. So yeah, here we are completing with the problem on influence line diagram of uh, overhanging beam. Okay, see you tomorrow at 4 o'clock for structural analysis subject. So we are going to take approximate method. Okay, approximate method, that topic we are going to study. uh, Thank you for listening. Thank you.